Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be covering Chapter 9 for our MCAT Physics and Math playlist, and this chapter is titled Atomic and Nuclear Phenomena. In this chapter, we're going to cover the following objectives. First, we'll start with explaining the photoelectric effect. Here we're going to define threshold frequency and we're going to examine the kinetic energy of ejected electrons. After that, we're going to connect this experiment to the double slit experiment from the previous chapter to better understand wave-particle duality. Next, we're going to discuss the absorption and emission of light. We're going to focus on how electrons transition between energy levels and how this relates to the electromagnetic spectrum. Third, we're going to cover nuclear binding energy and mass defect and explain how small changes in mass result in significant energy differences. Finally, we're going to look at nuclear reactions, including fusion, fission, and radioactive decay, to understand the processes behind energy production and nuclear stability. With that, let's go ahead and get started on our first objective. The photoelectric effect refers to the phenomenon in which electrons are ejected from the surface of a metal when it is exposed to light of a sufficient frequency. To fully understand this, we need to cover two properties of light: frequency and intensity. Frequency refers to how many wave cycles of light pass a given point per second, and it's typically measured in hertz. Light with a higher frequency carries more energy per photon compared to a lower frequency light. Intensity, on the other hand, describes the brightness of the light, or more scientifically, the total energy delivered per unit area per second. It depends on the number of photons striking the surface of the metal, but it says nothing about the energy of each individual photon. These distinctions are critical to understanding the photoelectric effect because, as the experiment showed, it is not the intensity that determines whether electrons are ejected or not. It is the energy of the individual photons, which is directly tied to the light's frequency. For electrons to be ejected from a metal, the photons must meet or exceed a threshold frequency. This is the minimum frequency required to liberate electrons from the metal's surface. And this value is, of course, unique to each metal. If the light's frequency is below this threshold, then no electrons are ejected, no matter how bright or intense the light is. And this is because in such cases, the individual photons lack the energy needed to overcome the binding energy holding the electrons to the metal. And this value is known as the work function. However, once the threshold frequency is exceeded, the behavior of the system becomes completely different. Now that the threshold frequency is met, we observe a couple of interesting things. First, the kinetic energy of the emitted electrons increases linearly with the frequency of the light. This means that higher frequency light produces faster moving electrons. The second point is that the number of ejected electrons, or the photoelectric current, this increases with the light's intensity. A greater intensity corresponds to more photons striking the surface and interacting with electrons. Now, these observations, they directly contradicted the predictions of classical physics. When they didn't know any better, classical wave theory proposed that light's energy depended solely on its intensity, meaning that brighter light should eject more energetic electrons regardless of the frequency. But alas, this theory couldn't explain why low-frequency light, no matter how intense, failed to eject electrons, or why the kinetic energy of the electrons was tied to the frequency rather than the intensity. This experiment, the photoelectric effect, demonstrated a significant challenge to classical theories, and it required a brand new explanation. So in 1905, Albert Einstein proposed a groundbreaking solution by introducing the concept of photons. Photons are discrete packets of light energy. Einstein suggested that the energy of a photon is directly proportional to its frequency. And this is expressed in this equation. The energy of a photon is equal to Planck's constant multiplied by the frequency of light. For an electron to be ejected, it has to absorb a photon with enough energy to overcome the work function of the metal. If the photon's energy exceeds this threshold, then the excess energy is converted to kinetic energy. And this can be calculated using this equation. So this equation says that the kinetic energy of the emitted electron, that's equal to the energy of the photon minus the work function of the metal. This equation explains why frequency and not intensity was the determining factor for whether electrons were emitted and why the kinetic energy of the electrons depended on frequency. Now, Einstein's explanation not only resolved the mysteries surrounding the photoelectric effect, but it also provided experimental evidence for the particle-like nature of light. This idea, combined with the wave-like behavior of light that was observed in phenomena such as diffraction and interference, introduced the concept of wave-particle duality. The wave-particle duality idea expressed that subatomic particles and light exhibit both wave-like and particle-like properties depending on the situation. This principle has since become a cornerstone of quantum mechanics. With that, let's jump into a practice problem. This problem says, if blue light of frequency 6 times 10 to the 14 hertz is incident on rubidium, which has a work function equal to 2.26 electron volts, will there be a photo ejection of electrons? If so, what is the maximum kinetic energy that an ejected electron will carry away? Here we're given Planck's constant in 2 different units. To determine if there will be a photo ejection of electrons, we need to calculate the energy of the photons. We can do this using the following equation. The energy of the photons is equal to Planck's constant multiplied by frequency. We're given the frequency of light, it is equal to 6 times 10 to the 14 hertz. And we're also given Planck's constant. We're given Planck's constant using 2 different units. Ultimately, the value for energy that we calculate, we want to compare to the work function of rubidium. The work function of rubidium is given in electron volts, so the version of Planck's constant that we want to use is the one that has electron volts in it. So Planck's constant is 4.14 times 10 to the negative 15 electron volts times second. When we calculate this, we get that the energy of the photons is equal to 2.48. And we notice this is greater than the work function, so that means there will be a photo ejection of electrons. Since there is, we need to answer the second part of the question, which is what is the maximum kinetic energy that an ejected electron will carry away? To calculate this, we will be using the following equation. The kinetic energy of the ejected electron is equal to the energy of the incoming photon minus the work function of the metal. So this is going to be 2.48 electron volts minus 2.26 electron volts, and this gives us a value of 0.22 electron volts. So that means the maximum excess kinetic energy carried away by the electron is going to be equal to 0.22 electron volts. With that, we can move into the second objective. Here we're going to focus on the concepts of absorption and emission of light. To start, we want to revisit the Bohr model. In the Bohr model, electrons occupy specific energy levels or orbits around the nucleus. These orbits are quantized, meaning that electrons cannot exist between them. They can only transition from one level to another by either absorbing or emitting energy. When an electron absorbs energy, it moves to a higher energy level, entering what is called an excited state. The energy required for this transition comes from a photon, whose energy must exactly match the energy difference between the two levels. This relationship is described by our favorite equation, E equals hf. E is the energy of the photon. That is equal to Planck's constant multiplied by the frequency of the light. On the other hand, when an electron returns to a lower energy level, it releases a photon with energy equal to the gap between the two levels. This process is responsible for the emission of light, and the wavelength of the emitted photon determines its color in the visible spectrum or its position elsewhere in the electromagnetic spectrum. These principles form the basis of absorption and emission spectroscopy. And spectroscopy is a really powerful tool for analyzing the structure of atoms and molecules. In absorption spectroscopy, we measure the wavelengths of light absorbed as electrons jump to higher energy states. We know that different substances absorb light at characteristic wavelengths, so that can then be used to identify them. For example, in infrared or IR spectroscopy, this is commonly used to study molecular vibrations because different bonds absorb specific wavelengths of IR light. In addition, UV vis spectroscopy examines the absorption of ultraviolet and visible light, and this reveals information on the electronic transitions that occur within molecules or atoms. Emission spectroscopy, on the other hand, focuses on the light emitted as excited electrons fall back to lower energy states. A familiar example of this is the emission of light by heated elements, like the bright spectral lines of hydrogen that are observed in flame tests. These lines correspond to the discrete energy levels of the electrons in the atom, and it reinforces the quantized nature of electronic transitions. Another fascinating phenomenon related to these processes is fluorescence. In fluorescence, a material absorbs high energy light, like ultraviolet radiation, and then emits it as lower energy visible light. This occurs because the absorbed photon excites the electron to a higher energy state, but then as the electron relaxes, some energy is lost as heat, so the emitted photon has less energy than the absorbed photon. And if it has less energy, it therefore has a longer wavelength. So even though a high energy light was absorbed, it emits a lower energy visible light. With that, we can move into the third objective. Here we're going to discuss nuclear energy and mass defect. So far, we've focused on the interactions between electromagnetic radiation and electrons. But now we want to turn our attention to the nucleus of the atom and the energy stored within it. To understand nuclear binding energy, We first need to examine what happens when protons and neutrons, collectively known as nucleons, come together to form the nucleus. When nucleons combine to form a nucleus, the system loses a small amount of mass compared to the total mass of the individual protons and neutrons. This difference is known as the mass defect. And while this may seem counterintuitive, it reflects a fundamental principle of physics, and that is that mass and energy are interchangeable as described by Einstein's famous equation E equals mc squared. The mass lost during the formation of the nucleus is actually converted into energy called the binding energy, which is released as the nucleons are bound together. Binding energy is crucial because it represents the energy required to break the nucleus back into its individual protons and neutrons. This energy arises from the strong nuclear force. This is the most powerful fundamental force in nature. Unlike the electromagnetic force, which repels positively charged protons from each other, the strong nuclear force acts over extremely short distances, and it holds the nucleons tightly together, and it stabilizes the nucleus. Without this force, the repulsion between protons would make the nucleus unstable and prevent atoms from existing as we know them. Now, here it's also important to recognize the role of the weak nuclear force. This contributes to nuclear stability in processes like radioactive decay. While it is much weaker than the strong nuclear force, the weak force is also essential for enabling certain nuclear transformations, which we're going to explore in the next objective. In summary, the mass defect and the conversion of mass to energy through E equals mc squared explain why nuclei are energetically favorable systems. The release of binding energy during nuclear reactions is also what makes processes like nuclear fission and fusion so powerful, because these reactions release vast amounts of energy when the nuclei are formed or split. With that, let's jump into a practice problem. This problem says, measurements of the atomic mass of a neutron and a proton yield these results. The atomic mass of a proton is 1.00728 AMUs, and the atomic mass of a neutron is 1.00867 AMUs. Now, helium contains 2 protons and 2 neutrons, which should theoretically give a helium nucleus a mass of 4.03190 AMUs. However, the true mass of the helium nucleus is 4.00260 atomic mass units. What is the mass defect and binding energy of this nucleus? Note that C squared is equal to 932 mega electron volts per AMU. To calculate the mass defect, this is just going to be the difference between the theoretical atomic mass for the helium nucleus and the actual atomic mass for the helium nucleus. We can easily calculate that as 4.03190 minus 4.00260. This difference gives us 0.02930 AMUs. So again, this value is the mass defect for the helium nucleus. This is the mass that contributed to the binding energy of the nucleus. So we're going to be using this mass to calculate the binding energy using Einstein's famous equation E equals mc squared. M is 0.02930 AMUs, and C squared is equal to 932 mega electron volts per atomic mass units. You notice AMU cancels out Our final answer is going to have units of mega electron volts, and we can do some approximating here to make the math easier. We're going to approximate this to 0.03, and we're going to approximate this to 900, and the multiplication of these two numbers gives us 27 mega electron volts. And with that, we've answered this problem, and we can move into our last and final objective. Objective 4 is all about nuclear reactions. Here we're going to discuss how these nuclei change under specific conditions and how they release a tremendous amount of energy in the process. To begin, let's recall the fundamental components of an atom. At its core lies the nucleus, and this is made up of protons that are positively charged and neutrons which are neutrally charged. Surrounding the nucleus are electrons, which are negatively charged, and they contribute very little to the atom's overall mass. The number of protons in a nucleus defines the atomic number of the element, and then the total number of protons and neutrons gives us the mass number. Together, these values allow us to represent an atom using standard notation, where the mass number is written as a superscript and the atomic number as a subscript next to the elemental symbol. So for example, we can do oxygen. The elemental symbol for oxygen is a capital O. In the upper left corner, we write the mass number, which is approximately 16 for oxygen. And in the lower left corner, we write the atomic number, which is 8 for oxygen. Now, nuclear reactions, they involve changes in the composition of the nucleus, and they're often accompanied by the release of energy. There are two main types of nuclear reactions. There's fusion and fission. In fusion, two smaller nuclei combine to form a larger, more stable nucleus, and it releases a tremendous amount of energy in the process. This is the reaction that powers the sun, where hydrogen nuclei fuse to form helium. On the other hand, fission is the process by which a large, unstable nucleus splits into smaller nuclei, and it's often accompanied by the release of neutrons and energy. Fission is the basis of nuclear reactors and atomic bombs. Another key concept in nuclear reactions is radioactive decay. This is a naturally occurring process where an unstable nuclei spontaneously emits particles or radiation to achieve greater stability. On the MCAT, you should be prepared to answer 3 general types of radioactive decay problems. The first type of problem deals with the integer arithmetic of particles and isotopes. The second type deals with radioactive half-life. And the final type of problem you'll encounter uses exponential decay curves and decay constants. In order to answer these question types, we have to understand isotope decay arithmetic and nucleon conservation. Radioactive decay often involves the transformation of one isotope, which we call the parent nucleus, into another, which we call the daughter nucleus, and in the process, there's the emission of a decay particle. These reactions follow specific rules of conservation. The first rule says that the total number of nucleons must remain constant. And remember, nucleons is another term for protons plus neutrons. The second rule says that the total charge must remain constant. For example, if an atom of isotope X with mass number A and atomic number Z decays into isotope Y, the reaction can be represented in the following way. This formula illustrates the balance between the parent nucleus, the daughter nucleus, and the emitted particle, and it ensures that the conservation laws are upheld. Next, what we're going to do is we're going to dive into the specific types of radioactive decay, alpha, beta, and gamma, We're also going to discuss electron capture, half-life, and exponential decay. So let's go ahead and get started with alpha decay. Alpha decay is a type of radioactive decay in which an unstable nucleus emits an alpha particle to become more stable. An alpha particle is essentially a helium-4 nucleus. It consists of 2 protons and 2 neutrons and absolutely no electrons. Because of its composition, the emission of an alpha particle results in a decrease in both the atomic number and the mass number of the parent nucleus. In alpha decay, the parent nucleus loses 2 protons and 2 neutrons, which reduces the atomic number by 2 and the mass number by 4. And this transformation is represented here by the general equation. Alpha decay is common in heavy nuclei such as uranium and radium because the strong nuclear force is unable to fully counteract the repulsive electrostatic forces between the large number of protons in these nuclei. So by emitting an alpha particle, the nucleus reduces its size and charge, and that increases its stability. Keeping that in mind, let's jump into this practice problem. This problem says, suppose a parent nucleus X alpha decays as follows. What are the mass number and atomic number of the daughter isotope Y? To reiterate, alpha decay is the emission of an alpha particle, which is a helium-4 nucleus that consists of 2 protons, 2 neutrons, and 0 electrons. The emission of an alpha particle means that the atomic number of the daughter nucleus will be 2 less than that of the parent nucleus, and the mass number will be 4 less. And that's what's expressed in this balanced equation. So for our problem, the daughter isotope Y is going to have a mass number of 234, which is 4 less than the parent nucleus, and it's going to have an atomic number of 90, which is 2 less than the parent nucleus. And so if we were to write this balanced equation, we would write our parent nucleus has a mass number of 238 and an atomic number of 92. It decays into the daughter isotope Y with a mass number of 234 and an atomic number of 90, and the alpha particle. Now, while it is not necessary to identify the elements to answer this question, answers on the MCAT are usually given with the element symbol. So here, the daughter isotope Y is going to be thorium because its atomic number is 90. So the daughter nucleus here is thorium with an atomic number of 90 and a mass number of 234. Beautiful. Let's go ahead and move into our next discussion on beta decay. Beta decay is a type of radioactive decay in which a nucleus emits a beta particle to achieve greater stability. A beta particle can either be an electron, denoted as beta minus, or a positron, denoted as beta plus. A positron has the mass of an electron, but it carries a positive charge. While electrons and positrons are not normally found in the nucleus, they are produced during beta decay as a result of the transformations that are happening among particles inside the nucleus. In beta minus decay, a neutron in the nucleus is converted into a proton, and in the process, it emits a beta particle, aka an electron. Technically, an antineutrino is also emitted in the process, but we do not need to worry about that for the MCAT. The equation for beta minus decay can be written in the following way. Here, the parent nucleus X transforms into a daughter nucleus Y, where the atomic number increases by 1 because a neutron has become a proton. The mass number remains the same because the total number of nucleons is unchanged. In beta plus decay, also known as positron emission, a proton in the nucleus is converted into a neutron and it releases a positron, which again, this is a particle with the same mass as an electron, but with a positive charge. Technically, a neutrino is also emitted in the process, but again, we don't need to worry about this for the MCAT. The equation for beta plus decay is shown here. In this case, the parent nucleus X transforms into a daughter nucleus Y, where the atomic number decreases by 1 because a proton has been converted into a neutron. The mass number, of course, remains unchanged. Let's go ahead and tackle a practice problem now. This problem says, suppose a promethium-146 nucleus beta decays as follows. What are the mass number and atomic number of the daughter isotope Y? This equation gives us a huge hint. This right here indicates that this is a beta minus decay. And in a beta minus decay, a neutron in the nucleus is converted into a proton, and then a beta particle, aka an electron, is emitted. Here, the parent nucleus transforms into a daughter nucleus, where the atomic number increases by 1 because a neutron has become a proton. So for the daughter isotope Y, the atomic number is 62. For a beta minus decay, however, the mass number remains the same because the total number of nucleons is unchanged. So the mass number of the daughter isotope Y is 146. Y here has to be samarium because its atomic number is 62. Therefore, the daughter nucleus here is Sm for samarium with a mass number of 146 and an atomic number of 62. Now we can move into gamma decay. Gamma decay is a type of radioactive decay in which an unstable nucleus releases energy by emitting gamma rays, which are high-energy photons. Unlike alpha and beta decay, gamma decay does not involve the emission of particles such as alpha particles or electrons. Instead, it involves the release of electromagnetic radiation as the nucleus transitions from a high-energy state to a lower energy state, similar to how electrons emit light when they fall to lower energy levels. The equation for gamma decay is typically written in the following format. Here, X star represents the nucleus in an excited state, and X is the same nucleus in a lower energy or ground state after emitting a gamma ray. So to reiterate, gamma rays are part of the electromagnetic spectrum, and they have no charge or mass. This means gamma decay does not change the number of protons or neutrons in the nucleus. The atomic number and mass number remain the same, making gamma decay purely a release of energy. Let's go ahead and tackle this problem. This problem says, suppose an excited parent isotope, gamma, decays, and then undergoes positron emission, and then in turn, alpha decays. If Z is americium-241, what is X star, and what is the mass number and the atomic number? Since we're given the final daughter nucleus, we're going to have to work backwards through the reactions. The last reaction that happens is the alpha decay, and we're told what the daughter isotope for this alpha decay is. It's americium-241, and from here we just have to work backwards to figure out the parent nucleus. To do that, we have to add +4 to our mass number and plus 2 to our atomic number. So our parent nucleus for this reaction is going to have a mass number of 245 and an atomic number of 97. Now this is berkelium-245. Now the preceding reaction before that was the positron emission. We figured out our daughter nucleus for this reaction. It's berkelium-245. How do we figure out the parent nucleus? Well, this is a beta plus decay. In a beta plus decay, the mass number remains unchanged. So for our parent nucleus, it will still have a mass number of 245. To figure out the atomic number, though, for our parent nucleus, it's going to be plus 1 to the daughter nucleus's atomic number. So for this, we're going to have a parent nucleus with a mass number of 245 and an atomic number of 98. Now this is californium-245. For our final preceding reaction, we have a gamma decay, right? This is where we started, but since we were given the final daughter nucleus, we've had to work backwards to the first reaction that happened so we can figure out what our excited parent isotope X star is. Now, for this part, it's just a gamma decay. And a gamma decay is just a type of radioactive decay in which an unstable nucleus releases energy by emitting gamma rays. Gamma rays are part of the electromagnetic spectrum, so they have no charge or mass, and that means gamma decay doesn't change the number of protons or neutrons in the nucleus. So for this final reaction, if we're trying to figure out the parent nucleus from the daughter nucleus, for a gamma decay, it's going to be exactly the same thing. It's going to have the same mass number and the same atomic number. That means that the atomic number of the parent nucleus is 98 and the mass number is 245. This is a higher energy form of californium-245. So this is X star and its mass number and its atomic number. Wonderful. Now let's discuss electron capture. Electron capture is a type of radioactive decay best thought of as the reverse of beta minus decay. In electron capture, a nucleus absorbs an inner orbital electron and it combines it with a proton to form a neutron. This process reduces the atomic number of the nucleus by 1, but the mass number remains unchanged since no nucleons are lost or gained. And the general reaction is represented in the following way. X is the parent nucleus, E represents the captured electron, and Y is the daughter nucleus. So to reiterate, during electron capture, an electron interacts with a proton in the nucleus to form a neutron. Now, technically, a neutrino is emitted to conserve energy and momentum, but like I said earlier, we're not concerned with that part for the MCAT. Now I want to segue into half-life. Half-life is a critical concept in radioactive decay, and it describes the time required for half of the atoms in a radioactive sample to decay. This property is unique to each radioactive isotope, and it is independent of the initial amount of material. The half-life provides a predictable timescale for the decay process, and it follows an exponential decay model. But before we elaborate on that, let's do a quick conceptual problem. This problem says, if the half-life of a certain isotope is 4 years, what fraction of a sample of that isotope will remain after 12 years? If 4 years is 1 half-life, then 12 years is 3 half-lives. So during the first 4 years, during the first half-life, half of the sample will decay. You'll be left with only 1 half. During the second half-life, so this is years 4 through 8, half of the remaining half will decay, so you're going to be left with 1/4 of the original sample. Then during the third and final half-life, so years 8 through 12, half of the remaining fourth will decay, and that leaves you with 1/8 of the original sample. Thus, the fraction remaining after 3 half-lives is just 1/2 raised to the power 3. So 1/2 cubed, and that is equal to 1/8. So again, you'll be left with 1/8 of the original sample after 12 years. Now we can cover our last and final topic for this chapter, and that deals with exponential decay. To begin, let's define N as the number of radioactive nuclei in a sample that have not yet decayed. The rate of decay of these nuclei, denoted as delta N over delta T, this is directly proportional to the number of undecayed nuclei remaining. So we can write this expression in the following way. And here, lambda is the decay constant. This is a value unique to each radioactive isotope that quantifies how quickly the nuclei decay. In addition, the negative sign indicates that the number of undecayed nuclei decreases over time. By solving this differential equation, we arrive at the exponential decay formula that you see here. In this equation, N naught is the initial number of undecayed nuclei at time t equals to 0. N is the number of nuclei remaining at time t. E is Euler's number, and it's a mathematical constant that's approximately equal to 2.718. And this formula tells us that the decay process is exponential, meaning that the number of undecayed nuclei decreases by a fixed proportion over equal intervals of time. Here, lambda, again, is our decay constant. T is time. Now, there's also a relationship between the decay constant and the half-life, and that relationship is demonstrated here. The decay constant is equal to the natural log of 2 divided by the half-life. Natural log of 2 is equal to 0.693, so we can alternatively write that the decay constant is equal to 0.693 divided by the half-life. And this relationship links the two key parameters of radioactive decay, the half-life and the decay constant. To summarize, the exponential decay model allows us to predict the behavior of radioactive substances over time. So whether we're calculating the remaining quantity of a radioactive sample or we're determining the time required for a specific fraction to decay, these equations provide a reliable framework for understanding and quantifying radioactive processes. So let's go ahead and do our last and final example problem for this lecture. This problem says, if at time t equal to 0, there is a 2 mole sample of radioactive isotopes, how many nuclei remain after 45 minutes, assuming a decay constant of 2 inverse hours. And also here we're given an important piece of information. E to the negative 3 over 2 is equal to 0.22. This problem is a direct application of the exponential decay formula. Here we're given the decay constant and we're given the time, so we can go ahead and plug those variables in. Our decay constant is 2 inverse hours, and our time t is 45 minutes. We can express this as 3 divided by 4 hours. This way, hours cancel out, and what we're left with is n is equal to n naught multiplied by e raised to negative 3 over 2. Now, e raised to negative 3 over 2 is equal to 0.22. We're given that in the problem. So what we're left with now is n equals 0.22 multiplied by n naught. This means that 22% of the original 2 mole sample remains after 45 minutes. So this is equal to 0.44 moles. From there, we can go ahead and calculate the number of nuclei remaining by multiplying by Avogadro's number. When we do this, we get 2.64 times 10 to the 23 nuclei. This is what remains after 45 minutes. And with that, we've completed this chapter. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.